Here's a related rate problem that's on the final exam review for my Calculus 1 class. So I'm going to, again, do this two different methods, and as a student, you can pick which one makes the most sense. One uses the chain rule, and one uses implicit differentiation. And they both work. So here we have a chemical storage tank in the shape of an inverted cone with depth 12 meters and top radius 5 meters. When the depth of the chemical in the tank is 1 meter, the level is falling at 0.1 meters per minute. How fast is the volume of the chemical changing? So I try to teach my students, they need to draw pictures, they need to write down what's given and what you want. It helps to, again, the idea of relating everything together one way or another. So if I have inverted cone, and yes, it's supposed to be 3D, but it helps in this case to not draw it necessarily that way. My radius here is 5. My length here is 12. And the chemical is draining out of the tank. So I'm just going to put some random height of the chemical here because we don't know exactly how high it is. And then at that point, there is a random radius that we don't know either. Now, as that water drops, I do have some information that I have been given to me. So what's given here? I know that when the depth of my tank, or when the height of that chemical is 1 meter, then the level is falling at 0.1 meters per minute. So my level H is falling 0.1 meters per minute. So meters per minute to me would be dH dt in this case, meters per minute. Change in meters per minute, change in height, change in depth per minute. That's given to me as 0.1 meters per minute. Sorry, that's a 1. And this is meters here. Now what I want is how fast, which is a time element, is the volume of chemical changing. So that's a rate. I want to know how fast is the volume changing. So I'm trying to find dV dt. I'm given this information here, and I have this picture here. In this picture, I should relate somehow V and H together. Now, in general, the volume of a cone is 1/3 of the volume of the cylinder that the cone came from. So it's 1/3 pi r squared h. I know that's kind of funny. It's always true, though, by the way. If you have a right circular cone that's used to be part of a cylinder, it's always 1/3 of it. You can fit 3 cones in a cylinder. That's just beside the point, but that's kind of cool. It's a helpful way to remember the formula. So here's our volume. It does relate H and V together. Again, we're relating related rates. It does relate V and H together, but I have this extra R here that I need to not eliminate, but write as a function of H, so that V is just a function of one letter because I don't have much information here about R. So I'm going to use this picture here. It's a similar triangles. We got, if I draw a line down the center, similar right triangles. So this little triangle down here is similar to this triangle up here. So the sides are proportional. That means that R is to 5 as H is to 12. And since I want V as a function of H, I do want to substitute something in for R. So in this case, solving for R, I get R equals, multiply both sides by 5, 5H over 12. So in my volume formula, I'm going to rewrite 1/3 pi R, which is 5H over 12, squared times H. Sorry. I'm going to replace R here with R here, and then I'm going to simplify. It always helps to simplify. Students don't like simplifying, but I tell you what, it really does help at times. So if I square this, I get 25 H squared over 144 times H. And if you know that you're going to have to take the derivative of that eventually, it's best if you push all the constants to one side. So I have 25 pi divided by 3 times 144. I'm not even going to bother doing the math yet. Times h cubed. H squared times h is h cubed. So there's my relationship between the volume and my height or depth of the chemical. And that's exactly the two letters that I want to relate together. And we'll come back to this. I guess I could write this up here now so that I can always reference it. 25 pi divided by 3 times 144, which, by the way, doesn't have anything pretty simplified. So again, I'm just going to leave it like that. And I'll reference that here. So method 1 uses the chain rule. So if I want dV/dt, that's my goal, I want to somehow relate a rate to dH dt, so in the end I get dV/dt. So I know that if I have dH dt here, I need to have a dH here so they can kind of quote-unquote cancel. They're not really doing that, but and then once they're gone, I need to have dV dt left. So if dH dt go away, the product leaves me with dV dt, so there's my related rates. Now I just have to put in these different numbers and solve for the thing that I want. So dV dH, well, I can come over here and calculate dV dH, pretty straightforward here. So that's going to be 25 pi 3 times 144. Since that's a constant, I just don't worry about it. Then I take the derivative of that, 3h squared. Notice those 3's go away. So I'm left with 25 pi over 144 times h squared. So I'm going to put that in here. 25 pi divided by 144 times h squared times dH dt. Now, the information that's given to me when h equals 1, dH dt is equal to 0.1. So now I'm going to plug all that in to finally come up with my number for dV dt. So that's 25 pi over 144 times 1 squared times 0.1. And let's see what that number comes out to be. Clear out my calculator. So let's see. The numerator is going to be 25 pi times 0.1, and the denominator is going to be 144, right? 25 pi, 0.1 over 144, and I'm getting 0.545. Let me see this again. 0.0545. 0.0545. Now that's the number I get up. Now I'm doing dV dt, so that's unit of measure. If this is meters per minute, volume is cubic meters per minute. So it's going to be meters cubed per minute as my unit. Now, in class, many of my students recognize that this is a decreasing rate, correct? Because here my H is decreasing and my volume should be decreasing at the same time. Because H is decreasing, this rate, you can start out with it being negative, and then your dV dt turns out negative at the same time. But in this case, I would just say the rate at which the volume is dropping is negative, and you can just add that in the end. I don't know. I don't know what your teacher would say. I don't mind you guys adding it at the end. That's okay. And then you would need to say because V is decreasing. Right. That's method 1. Now method 2 in this problem isn't that big a deal because of the beauty of our function that's relating everything together. So method 2 uses implicit differentiation. So I have this relationship that we built. V equals 25 pi over 144 times 3 h cubed. that was given to us up here. We found it, that relationship, and I'm rewriting it down here. So if I'm looking for dV/dt, the implicit differentiation will say, well, now that I have this direct relationship here, I'm just going to take the derivative of both sides with respect to t. So the derivative with respect to t of v equals, now since that's a constant, I don't have to worry about taking the derivative of it because it's multiplied by that number there. So 25 pi, 144 times 3, times the derivative with respect to t of h cubed. Derivative with respect to t of v is dV/dt. And over here I have 25 pi divided by 144 times 3 times, now the derivative of h cubed with respect to t is 3h squared dh dt. Using implicit differentiation, remember? These 3's will go away, always simplify. And I know that when h equals 1, dh dt equals 0.1. And you can put negative 0.1 in there too. That's fine. Let's do it on this example. So then in the end, dV/dt is equal to 25 pi over 144 times 1 squared times 0.1. And if you notice, that's exactly what we got right here. So this becomes negative 0.0545 cubic meters per minute. Let me put my negative in here to be proper. All right, again, the methods turn out exactly the same. It depends on your power as a math student, your superpower. Do you have a superpower in relating rates together using chain rule? Or do you have a superpower using implicit differentiation? Either way, the beginning structure is the same. You have to know what you're given, what you want, and how everything is related together in the problem. In this case, because v was a function of two variables, I had to change that. Otherwise, our methods don't work. We're only in Calc 1. We don't know multivariable yet. Nevertheless, there you go.